All right, I think we're finally ready to go here. Sorry about the delay. It seemed like it was taking a long time to get this to jump up. All right, so we were talking about a coordinated turn, and we defined a coordinated turn as being no side force. Wow, there's a huge lag in here. Let me check which Wi-Fi I'm hooked up to. Somebody pull up the syllabus for me. Anybody have a copy with them? Pull it up. The syllabus, I forgot to look at it. It says on it what it covers. It says exam 2 up to and including, and I forget what it says. So we'll answer that question when somebody gets up to it. So we're going to look at the coordinated turn equation here. And we're going to look at solving for R from this. And then plugging in the values, the expressions from the kinematic equation, and express R and theta in terms of bank angle alone and in terms of load factor. So that's what we're going to do starting out today. It says up to and including longitudinal trim. So that's what it will include. I'm sorry, I wrote that a month ago. I didn't memorize and I forgot to look at it. So that's what we're doing. So then this is correct here. So the coordinated turn equation the left half of it says 0 is mu1 r1 minus mg sine phi1, and we're going to use this to express r. And then the right-hand side of the equation is the expression for the side force coefficient, and we'll use that to solve for beta, aileron, and rudder. Looks like technology, at least this afternoon, is my nemesis. Tuesday, it was some strawberries I was cooking on the stove that I forgot about and they burned. And then I accidentally put a Ziploc bag on the hot burner and it melted and it went downhill from there. We won't talk anymore about that. But let's see if we can keep the technology together. Yeah, we have leftover strawberries, so I'd cook them and put some sugar in it, and I got strawberry jelly. It's pretty good. It's the strawberries that are not ripe, not good enough to eat anymore. Anyway, so R1 is G sine of phi1 over U1. And I'll show you at the end of the lecture that we can express this in terms of load factor. like that, but we're going to show that later. We will use it. It's not hard. You express cosine phi in terms of 1 over n, and you do some algebra and trig, and you're good. Okay, also from the kinematic equations, we have Q1 in terms of the turn rate. And we have R1. I'm going to write this backwards because I want to write something over to the right. So this is where we took the fact that we had, this is essentially expressing that vertical z direction psi dot in the body fixed axis system. So that goes with the figure that we drew, and it just comes straight from the kinematic equations as well. And so then over here I'm going to write the value for R1, the expression for R1 that we got up here. So we're going to use this here. And this is good for R1 because it's in terms of bank angle or load factor. But we can use this to get Q in the same variables. Q will be in terms of bank angle or load factor. So if we substitute for psi dot there, then we're going to get a sine squared in the numerator from here, a U1 in the denominator, and we'll get a cosine in the denominator, because we're going to divide by that. So you can get Q1 in terms of bank angle. And then if you do algebra, which I'm going to show you later, you can get this in terms of load factor as well. And on an airplane, those variables are a bit easier to measure than turn rate. Load factor, you can measure with an accelerometer. Bank angle, you can just look at the artificial horizon and you can see what your bank angle is. And you could derive turn rate from that, from those basic variables. All right, so this expression and this expression will be substituted into the equations of motion, where we have those terms, R1 and Q1. So the equations that are left, the lateral directional equations, we're grabbing those out of the set that we looked at last time. So that's the right side of the coordinated turn equation, or it's the side force equation. So this comes from the lecture last time. Let me scroll up and see if I can find it. Again, so that comes from this part, which came from, keep going backwards. I think I have it on this screen. No, I showed it to you from the book, right? So let me pop that up. I'll get back here so you can copy on this. So that's from the side force equation, which came from I'll find it, I promise. Came from these equations here. These are the longitudinal and lateral directional equations. This is the drag, the X force equation here. This is the Y force, the Z force. So this is the equation that led to the definition of coordinated turn. And then we're grabbing the rolling moment and the yawing moment equations here. So these are copied out of your book. Remember, we took the full nonlinear equations and then we plugged in the forces and moments on the right side to specialize them for the turning flight. So I just wanted to remind you where those came from. Okay, so back to here. So this is the side force equation. And then the rolling moment equation. Oh, by the way, we'll divide both sides by Q bar S. Cancel that out. And then the rolling moment equation. So you can see the rolling moment equation. Here is the rolling moment coefficient due to beta, aileron, and rudder. And this is that extra term, remember, we added in because of the yaw rate R. And then this comes from the left-hand side of the equation due to the fact that we have R and Q values. And then the last equation is the yawing moment equation. And again, you can see where this one comes from. This is the yawing force coefficient, yawing coefficient, moment coefficient. This is the extra term we added into that. And then this comes from the left-hand side, which is the dynamics of the equation. So these are our three equations and three unknowns. And you can see why we needed to develop those expressions for R1 and Q1, because we need to plug those in everywhere you see that in these equations. Because those rates are determined by the bank angle or the load factor. In this case, we're going to leave it as bank angle for the turning flight. So this is real close to a matrix format. We've got all the unknowns on the left side. We got the right-hand side. So if you put this into a matrix format, you get the matrix on page 227. So it's going to be CY beta, CY delta A, CY delta R in the first row, this in the second row, this in the third row. So let me share that screen. Trying to figure out why it's not showing my PDF here. Let me try the other computer. All right, so here we go. Got this pulled up. This is that matrix from those three equations and the three unknowns. And you can see all the sines and cosines of phi in here, and those came from substituting in for R1 and Q1 with those formulas. So let's recap. Went back to the chapter 1 and got the steady state equations that are good for every flight condition, steady state. We specialized it for turning flight, which meant that P1 is 0, but then Q1 and R1, there's a yaw rate and a roll and a pitch rate as the airplane goes through the turn. So we use the kinematic equations and the coordinated turn equation to figure out formulas for R1 and Q1. Then we substituted into those three equations, and this is the set of equations that you get. And in the homework that you'll be doing next, the following to the one that's currently assigned, is you'll be solving this using MATLAB, and we're going to do an example of that. The book shows solutions using Cramer's rule, and they're perfectly valid. You have to calculate the determinant of that big matrix, and then this is the top matrix in Cramer's rule. So you can hand calculate, plugging in all these numbers here, but we have the power of MATLAB, so I think it's easier, and that's what you'll do in homework, is to just plug the numbers into this matrix, go into MATLAB and solve it. It's easier. So we have an example where we're going to plug numbers in for a 2G turn, which is a 60-degree bank angle. This is the lateral directional equations, and they're decoupled because phi is specified, so that's on the right-hand side. And then the next set of equations that we need to do are the longitudinal. We need to solve for alpha, elevator, and thrust. So here's the second of the second set of 3 of the 6 degrees of freedom. We have the drag equation, the lift equation, and the pitching moment equation. And notice he's already substituted in for P, Q, and R. Actually, P is 0. In terms of sine phi and cosine phi. But when it gets solved, we replace those with those expressions for load factor, because that's easier to do. And I'm going to write that set of equations up here that includes load factor because we need to work on it a bit. But I'm going to point out a typo. You see this 0 over here? I'm going to write this same equation on the screen here in a minute, and there's a term missing here. And it's minus m v1 r1. Minus m v1 r1, so make a note or write in your book. But I think what he's done is here he's assumed that v1, which is the side velocity, is small. But following the derivation, he doesn't say that at this point, so there really should be a minus m v1 r1 here. we need to jump back to this, but I want to develop that for a bit. So let me jump back to the other screen here. Looks like I have to stop sharing here. Now we're doing the longitudinal equations. So here's that equation with the term on the right, on the left side. So that's the drag equation. And again, you can look at this and go, yep, there's the drag, linear drag model here. There's the thrust force in the forward direction. And then here is an extra term that we didn't have for rectilinear flight because this is for turning flight. And then the last one is the pitching moment equation. And I see a mistake I made. I have a C-bar where there shouldn't be one. This C-bar should be gone because that's the lift equation. Everybody see where that was? It was right here. So there's our unknowns. Angle of attack, elevator, thrust or throttle. So we look at this and we realize that we have the same issue we had with cruise flight, because here the unknown alpha is inside the sine, and here it's inside the cosine. So think back, or look back in your notes and say, well, how did we fix that last time? Do you remember? This is for the cruise condition. What did we do? Yeah, we said some things were small, right? We said alpha was small, so we could knock this term out. And we have the cosine up here. We'd be tempted to say that's 1, but we have to use all 3 equations. And remember, we were able to knock it down to a 2x2 solution. And that's because we said, well, this is small too. So that allowed us last time and this time to solve just the bottom 2 equations by themselves for alpha and elevator. And then we go back up to the drag equation when it's all done, and then we solve that for the thrust. And we can leave this cosine in there because we already know alpha. So exact same strategy here. So we put this into a matrix. It's pretty straightforward. We identify the unknowns, alpha and elevator. Put those on the left side, put everything else on the right side, and we get a matrix problem that now has additional terms in it, like Q1 here and Q1 here that we're going to have to substitute for. Oh, and an R1. I knew I was missing something. So all that stuff gets shoved over to the right side. So here we're making an approximation. It's always good to keep track of what assumptions we're making. We're saying that dt is small and alpha plus phi t is small. If either of those are not true, then we can't do this. If we're flying at a high angle of attack, we got to use the full 3x3 solution and transcendental. So let's write out the matrix problem here. So there's the stuff that multiplies alpha and delta E. There's a whole bunch of stuff on the right side here. So there's all those extra terms. There's the extra term with Q in it right there. I lost a term. There should be also in this top line. That term there. Where? Divided by Q bar S. Let me see if I can fix that. Turns out that we can make some additional assumptions. We can say that this thing down here is small. Notice that it has this IXZ. That's the cross product of inertia. Typically that's small, so we can throw that out. And then it turns out that CLQ is usually small, so we can knock that out. Everything else we know these numbers. These are just properties of the airplane. We plug in for Q in terms of load factor. We can plug in for Q in terms of load factor here. But turns out that we can take these two terms and add them together and simplify this. So that's the last piece that we need to do before we have a solution for the longitudinal. All right, so there's that equation. And I want to work on the M U1Q plus M G cosine phi. And this is where we're going to plug in for Q. So I'm going to substitute that expression for load factor for Q. This came from a couple pages back. And then cosine of phi is 1 over load factor. So we're going to throw that in, cancel the U1 out here, and notice that there's an mg 1 over n negative over here, and mg 1 over n positive here, so those two cancel out. And that helps out a lot, doesn't it? Because it means that here we have mg over q bar s times load factor. And this is just CL1 or CL trim for level flight. Weight divided by q bar s. So he defines this. That's just the lift coefficient you would need if you were not doing a turn, if you were just doing level cruise flight. So that's the equation that we see, the matrix problem that he presents in the book. Right here. And that's what we need to solve. So again, Kramer's rule, simple 2 by 2, Kramer's rule just like we did before. In fact, you guys did that for a homework, right? Or are you doing that for a homework? Yeah, you're doing that on the homework. And so this is the solution here. What's different about this solution for alpha and elevator versus the one for longitudinal flight? So look at that carefully while I find the other solution here. Are you ready? Look at that one. We'll flip back and forth here. Yeah, so here's the solution to compare. Okay, you ready? We're going to find the planet Pluto. Why do I say that? The way they, well, it's not a planet anymore, or is it? I don't remember anymore. The way they found the planet Pluto, they called it Planet X. They knew there were gravitational disturbances on the other planets, Uranus and Neptune. And so they took photographs of the sky and the stars over various nights, and then they looked for a moving object because the planet moved relative to the stars and the stars didn't. And the way they did that was they had a special microscope that would allow them to view both images at the same time, one tonight and one a month later, and it would flip back and forth, and they were matched, and they would look for a spot that jumped back and forth when they flipped the pictures back and forth. Does that sound like a fun job? So night after night, they'd sit there flipping back and forth between pictures of the night sky. And somebody became famous because they found the dot that moved. So that too can be you. Or maybe you do something more exciting like go to Mars, right? So we're going to do that here. These are the equations for cruise flight. Here's steady state turn. Maybe I need to get them lined up better, huh? Let's move this down, make it bigger. Okay, ready? Rectilinear flight, turning flight. Rectilinear flight, turning flight. Rectilinear flight, turning flight. Anybody spot Pluto? Where are we? So here, and that's got load factor in it, right? So this is for rectilinear flight, load factor of 1. So what happens if we say load factor is 1 here? You get 1 minus 1 over 1. So that term's gone, and so you spotted one of the terms. What about, what else? Let's flip back and forth. Find Pluto. Guys seeing another change? This is also like the deal that they still put in the comics, right? What's different? You guys notice this term here? That's gone too, right? Because n minus 1 over n. And then look at the n here. There's CL1, there's n CL trim, which is CL1. So in fact, you can take this set of equations and plug n equal 1, and you get this because straight level cruise flight is for load factor of 1. All right, so now we have a solution for the steady state turn. It includes CMQ because this is Q here, and also Q is here. So that's why those terms are here. We're going to need this equation for elevator in a minute as well when we talk about, well, how does the elevator change when we do a turn? But now I want to do an example. So this is going to take a little bit of time, but I want you guys on your piece of paper to write down these two equations on your notes right now. I'll give you a few minutes. And then I'm going to give you the numbers to plug in. So I shouldn't have all the fun and do all the talking and work, right? So you guys can do this. Everybody good? So now I'm going to give you the numbers that go in here. The first thing we're going to calculate is gee, I can't talk, the denominator. So get ready to calculate this and we'll compare answers. And then we'll parallel process this. Everybody sitting on the tables where I am are going to calculate alpha. And everybody over there is going to calculate elevator. Good? And when you plug in numbers, I want you to leave n as a variable. Plug in all the other numbers and calculate the numbers that go in here, but leave n as a variable because I want to plug in n equal 1, and I want to plug in n equal to 2. Everybody on the same page here? All right, so we need the numbers from the back of the book. Appendix, this is airplane A. In cruise, there's the answers. Don't look at that. This is the Cessna 182 approximation. We're going to use the cruise condition here, so we're going to do a turn at 5,000 feet. And I've forgotten, do we need any of the inertia terms? No, we knocked that term out. Okay, so what we need are the numbers in that middle column. So I've even highlighted it for you. There's CL1, that's CL trim in the equation. So do the denominator first, and we'll calculate that, compare answers.
To calculate the denominator, don't we need the lateral coefficients as well?
You guys, the what? Oh, CM delta, yeah, those are down further. So let me scroll down to that. So what value are you getting for the denominator? Somebody brave enough? Shout it out.
Negative 4.68.
4.68 negative. Is that what everybody has? So we agree on that. So again, this table do alpha. Tables over there do elevator delta E. It's going to take a little bit of time, and then write the numbers in, leave n as a variable, which is going to make it easier, and then plug in n equal 1 and n equal to 2.
Do we assume the
Somebody's
incident
asking
angle
about
as 0?
IH. Yeah, we're going to assume IH is 0. So that makes it even easier. It knocks that term out. You guys remember what CL1 is? Because you're going to need that. Let me scroll up, get that copied down. It's 0.307. I think that's the only thing you need from up here. Everybody got that? CL1. Okay, so let me go back down. The what? Oh, star and we want to need that. It's on the previous page. So everybody ready for me to scroll so you can get that information? So here's U1, 220.1, and C bar is 4.9. I'll go back down and give you the data again. Everybody got that down? Sorry about that. At this point, you might be saying to yourself, wow, it would be a lot easier just to calculate the values in that 2x2 matrix and use MATLAB to solve it, right? Which would be totally true. In fact, if you're going to do this very many times, you would code the numbers into MATLAB, create that matrix, and if you had to change any of the variables, you could leave them as variables and just have MATLAB enter the values, ask you for them, and you could solve it inside MATLAB. But there is something to be gained from these closed form solutions, is that we'll eventually look at elevator per G, and we can take the derivative of the elevator equation with respect to load factor and calculate that directly. So how's it going? How's the alpha table going? In a minute, I'll write those numbers up here. Yeah, in a minute, I'll write up numbers here. I want to make sure everybody can get this. But so you have a solution? How about the delta E table? You guys working? So the load factor 1 equation is easy to do because you lose a term or two in there, right? In fact, the hardest one to calculate is gone. You guys still need the data here? Anybody still needing to look that up? And there's a lot of numbers in here, so if we get enough people matching the number, it's going to be quite amazing, actually. I think the first time I did this, it took me several tries. All right, I'm going to share my notepad so I can start writing as soon as I stop sharing this. So it's okay to take this away, the number sheet. And again, here's what I'm talking about. This matrix problem, probably much easier to stuff numbers in here, 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 and here, and calculate the numbers over here and tell MATLAB to solve it, although this takes some work over here as well. All right, let's give it a shot. So load factor equal to 1. I want to calculate alpha and delta E. Let's see how we're doing. So the alpha table, you have to shout. 3.2. How about other people? How about the elevator tables? Everybody's avoiding eye contact here. Does anybody over there have a number they're willing to share?
I got 0.0377.
What did he say?
I got 0.0377.
Is that in radians or degrees?
Radians, I hope.
Is that for elevator?
Yeah.
3.16 for what? We're not agreeing on the load factor equal 1. So on Zoom, what were you saying you got for elevator? Say that again.
I got 0.0377.
I'm getting for, let's see, I'm getting for alpha, I'm getting 0.21 degrees. Or minus 0.004. Maybe I need to check my work. Tell you what, you guys have the data. We're almost out of time. Go home and punch the numbers and come back next time and we'll start here. Here's what I got. So validate my work. So alpha, let me get this written clear. So you can check your answers, make sure I'm right. No guarantees here. So I got for no load factor, minus 0.004. radians are minus 0.21 degrees. So check me out because I don't know if this is right. There's a lot of numbers. And then for elevator, I get 0.1073 radians, or 6.15 degrees. So let's start here next time. Go home, get numbers for alpha and elevator with load factor and without. See if I've got the right numbers here or not, and we'll debug that next time. Oh, announcements. There's a homework due on Tuesday, and that includes that MATLAB Simulink stuff that you'll be doing with your trim solutions. So that's due on Tuesday. You guys turned in your flight assessment today, right? Your flight test assignment. And then we're having the exam on Thursday. Again, it's a 30-minute exam. We'll go quick. Remember to bring the parts of your book that you need for that. And if you need any airplane data, I'll let you know which part of the appendix that you need for that. All right, have a good weekend.